Goedenavond. I'm going to speak in English, so good evening, everyone. My name is João Trabucho. I guess a different name for this talk this evening could have also been what does knowledge of time on geological timescales teach us about our place on Earth, in space, in the universe, and perhaps in the Anthropocene? And I'd like in the next, 24 and a half minutes, explore that idea with you. So let's start at the beginning. Sigmund Freud once wrote that humanity had had to endure from the hands of science 3 great outrages. The first outrage was a Copernican one and basically was removing the dominion of man, let's use man with capital letter M, from the center of the universe, and displace the sun into it. And later, we even discovered that even the sun is just one star among a vast multitude of others. The second great outrage was Darwinian, and basically we were placed among the animals. We were mere hairless primates, and not this special creature created to the likeness of God to rule over the other animals. And then the third one was of Freud's own doing, which was man is not a rational animal, and so he embedded us further in the animal kingdom by making us realize that we have an unconsciousness that we are actually not able to control. And, sorry. There we go, now. This is the right slide. And so, Stephen Jay Gould pointed out that Freud had forgotten a fourth outrage, the second, chronologically speaking, which was inflicted, if you want a hero, you can maybe use Hutton, the father of geology, traditional in the myth-making of geology, but perhaps collectively inflicted, which was the discovery of deep time. So just like the Copernican outrage had removed humans from the center of the universe and largely decreased the space scale of human dominion, the discovery of deep time basically removed man from the duration of Earth history into a final scene on a much longer drama. And so, whereas previously the whole of Earth history had been wholly, fully human, after a brief creative prelude of 5 days, and then humans had been there for everything, now we were just the sort of last species arriving after a quite exciting story. So how do we know about that story? How do geologists know about Earth history? Basically, we could say that Earth history lies beneath our feet, also here in Utrecht, like a stack of books. And that was a metaphor that was used very often by early geologists, and you can see that on the picture on the right, a stack of books, each with its title. And these titles were the old names for the rock units that they were studying. So you see the old red sandstone and the coal strata. And they were stacked, and you could measure them. There's a hand measuring the depth of the coal strata. And it's easy to see the parallel that geologists were making if you look at the picture on the left with the Grand Canyon, with these big layers telling stories of deep time that could be read and reconstructed quite accurately by geologists. Now, nowadays, it looks like this. Geologists have been able to reconstruct the history of the Earth, and pretty much like historians, geologists, we subdivide history into intervals. So just like a historian will talk about the period between 1837 and 1901 as the Victorian period, so do geologists, for example, in the green color on the second column, talk about the Cretaceous, which was between 145 million years ago and 66 million years ago. And pretty much like Victorian times had a certain dressing style and certain food and certain habits and vices, so do geologists recognize the Cretaceous by certain rocks, certain fossils, certain organisms, and a given type of climate. Beneath the Netherlands, the stack of books looks like this. We're looking here at a cross-section This is reconstructed from geophysical data that we shoot seismic waves into the ground, and then we see what it looks like when it comes back. And you can see on the right, you see Belgium and Limburg. And we're basically on the southeast tip of the Netherlands. You can see that on that little map there, the red line. And all the way in the middle, we have the coast with the Wadden Islands, and then we have the offshore in the North Sea. And Utrecht is indicated there at the top. You can see beneath Maasbommelhei. And so you can actually see that these books here in the Netherlands, they're actually tilted like this. And the rocks that are at the surface in Limburg, they're at about 2,000 to 3,000 meters beneath our feet here. So the coals of Limburg that were used are here at about 2 to 3 kilometers. And if you go further north, they're even deeper, 3 to 4 kilometers under Groningen, and they're the same rocks that produce the gas from the Groningen field. So first we had to burn them ourselves, and then the earth just burned them for us. So how old is Earth? This old. That's 4,000, it's easy to say 4.6 billion in English, miljard in Dutch, but I don't like to say that because, and you'll see why. I'll explain in a second. So I always say 4,600 million years. This is John McPhee. He's a professor of creative writing at Princeton University, and he's a staff writer for The New Yorker, an American magazine. And he wrote in the 80s in The New Yorker a series of articles about not so much geology, but about geologists. I highly recommend them. You can buy them as a book called Annals of the Former World. And he traveled across the United States in the 80s, across Interstate 80, and he made a trip across the Cretaceous, which is about 250 million years ago, hardly an eternity if you think about the 4,600 million years age of Earth. And in these articles, he coined the concept of deep time. And he writes, numbers do not seem to work well with regard to deep time. Any number above a couple of thousand years, 50,000, 50 million, will with nearly equal effect awe the imagination to the point of paralysis. The problem with millions and billions is that they're so divorced from our daily experience that even though we use these words, we don't actually understand what they mean. We have a feeling as humans for how long a minute is, 25 minutes, which feels like an eternity to me right now. 1 hour, 10 years, 100 years. But then even 500, 600 years ago, 1,000, how long is 1,000 years ago? We're not very good at that. A few years ago, when I still had Twitter before Elon ruined it, I took this screenshot. And this woman, she explained millions and billions in the context of money. And so she says that if you had £1 every 10 seconds, you'd be a millionaire within 4 months, but then you would have to wait 310 years to hit your first billion. And her idea was, what she was trying to explain is how obscene it is to be a billionaire, how much money that is. And we fail to realize that. We always think that a billion is just the next step from a million, but it really isn't. It really takes a long time. It would take you longer than the days that you have in your life to actually count to a billion, if you counted every second, if it were possible. So here's Stephen Jay Gould, who I already mentioned. And Stephen Jay Gould is a historian and philosopher of science, was. And he has the best metaphor for deep time. He paraphrases John McPhee's book, and he says, consider the Earth's history as the old measure of the English yard, from the tip of the nose of the King of England to the tip of his outstretched hand. One stroke of a nail file, and the whole of human history is erased. So let's have a look at that. That cartoon is actually me. You can see my hair. So here starts Earth history. And all of this, and if you want, you can accompany me. And if you don't like your neighbor, you can take this opportunity to slap them. And you look all the way, all of this time, all along my arm, there's actually no life of complex organisms on Earth, only microbes. So you can look at it and all these microbes. And it took all the way to the first knuckles for complex life to appear on Earth. And then it takes to the second knuckle for the supercontinent of Pangaea. Maybe you've heard of it. Well, all the continents were together. It takes all the way to that second knuckle. And then we turn our arm around, and that cuticle there, that's where the dinosaurs lived. And then you go all the way, and my nails were cut short on purpose for today. And the 0.03 millimeters of the tip of your middle finger's nail is human history. And if you hit it, if you strike it with a nail file, it's all gone. 0.03 millimeters is an order of magnitude smaller than a dust mite, which you can barely see with your naked eyes. That's how tiny we are. And in this big history, we go back to this diagram where you see all of the animals and all of the plants and all of the things that emerged. In all of this history, we are one of the last species to appear. And very often, particularly my colleagues from history, they will say that everything before writing is prehistoric. I disagree. Earth has had a history of its own without us. And I would argue that it's more dramatic than Game of Thrones. So how thick is the book that tells our story, the Anthropocene? And I'm using here the Anthropocene with a small letter A because I'm a geologist and we did not approve it. The vote failed. So it's not official, so we write it with small letter. So humans, modern humans, humans like us, they exist for 300,000 years. But maybe actually only 8,000 years, because the record of humans is really only 8,000 years when we really started doing stuff. Okay? So what does that look like? The best record of the Anthropocene, these are pictures actually from the formal proposals for the Anthropocene. The best record is the Palmer ice core, which was drilled through the ice sheet on Antarctica. And that's 30 meters. Compare that to the Grand Canyon, it's not very thick. And the problem is, in 400 million years, it will have melted. And there goes our story with it. The best rock record of the sort of history of us is a stalagmite. So this is one of these hanging things on caves, druipsteen in Dutch. And it's in Ernesto Cave in Italy, and it's 4 millimeters. That's our story. So these are extremes. There's other stories, and they're not as good, but we are centimeters thick. That's more or less, when people ask me, how thick are we? We're centimeters thick. But that does not mean that we haven't had an enormous impact. Our historic insignificance does not mean that it's not without consequence. And we all know that in a very, very tiny interval of time, we've been able to change the composition of the atmosphere. We're not the first animals that have changed the composition of the atmosphere, by the way, but we've changed the composition of the atmosphere. And at present, we actually move more sand than all of the rivers in the world combined. If you don't know, the most used resource, probably if people would ask you, what's the most used resource? Most people, I think, will answer oil or gas. It's actually not. The first one is water, and the second one is sand. Every one of you, if you live in the Netherlands, you use 25 kilos of sand per year. You can ask me why if you pay me a beer after the talk, and I'll tell you how you use 25 kilos of sand. And I'm going to be really drunk, so one of you needs to take me home. So the world is running out of sand. This is an exaggeration. The world is not running out of sand, but we do move a lot of sand. And so we have an enormous impact on Earth. So the question, of course, that emerges from this is, okay, very short, very big impact. Would we be able to find a record of a civilization like ours that existed for as long as ours 440 million years ago? So can we go to a place like Grand Canyon, and we take our hammers and our tweed caps and sandwich, and probably a grad student or two to do the hard work, and can we actually find the record of one of these civilizations? This question is an actual question that has been posed in the literature. This is called the Silurian hypothesis. The Silurian hypothesis, Silurian here is due to Doctor Who, BBC, where the Silurians, they're the first inhabitants of Earth. at least the first intelligent inhabitants of Earth. The Silurians here are named, I think, at least I hope, for the time period in Earth history, the Silurian, which was about 400 million years ago. And that time period is named for pre-Roman tribes in the United Kingdom. So a lot of these intervals in Earth history are named for places and tribes and that type of thing. Let's just go back one slide. Can I go back one slide? There you go. So the Silurian hypothesis was proposed by two astrobiologists, actually, not geologists. And the question that they were posing was, in space exploration, one of the big goals with the SETI program and more recent programs is to figure out, are we alone? Is there other life out there? And they were trying to explore ways of recognizing whether the odds that we would find other civilizations such as ours are bigger than zero. And one way of thinking about that is, well, previously we thought maybe there are not many planets surrounding stars. And of those planets, maybe not all of them, or maybe none, are in the so-called habitable zone. But then people started realizing, physicists, astrophysicists, the more they acquired data, that actually there's quite a lot of planets in so-called habitable zones. So maybe there's life out there, and maybe some of that life evolved into industrial civilizations, such as ours. But if there's only one of us here in 4.6 billion years, so in 4,600 million years, only one very advanced industrial civilization emerges, then the odds of finding that are smaller again. What we would want is loads of planets in the habitable zone, with each having, across their histories, several industrial civilizations that come and go, and maybe we will find one of these. And that's the essence of the Silurian hypothesis. So would it be possible to detect one of these here on Earth? So actually their thought experiment is actually this. Were there humans just like us giving talks at Tivoli Vredenburg 440 million years ago? And how would we know that? It's a really interesting study. And so these are a picture of geologists at work. This on the left is one of my graduate students, and he's drilling rocks. And there's some water to cool, and we're wearing safety stuff just for the picture. And we remove it because it's too hot to work like this. And so he's drilling. This is actually in a quarry in South Limburg. We're looking there, trying to figure out what's going on with the water, the nitrite in the water. And so what we do there is we drill, and we cannot take the whole quarry home. And so you have to have a sampling campaign. And you see that also on the right picture. There's my hammer, and there's a number of papers. The papers, you cannot see what they say, but they actually say 1 meter, 1.5 meter, 2 meter. And so we go there, and we make a log, and we describe the rocks, and then we go and sample them. We can drill, we can take by hammer rocks, and then we take them home. But what you cannot do is you cannot take the whole thing. So you will study some of it, and hopefully it's representative. So we have ways of dealing with that. We know how fast it's accumulating, and there's variations, and we try to accommodate those. But there's always be part of the story that's missing. To make matters worse, the rock record itself is very incomplete. You can imagine that if sediment would accumulate at 1 millimeter per year for 4.6 billion years, there would be much more sediment than there is on Earth right now. So erosion, the removal of the record, must play a very important role in keeping things going. Our planet is a dynamic planet. The plates at the surface, which are sort of the crust of the Earth, they subduct, they go down into the mantle, things are destroyed, things are recycled, volcanoes cover stuff. So in this dynamic, we sort of have a number of books that are like, geology is like reading a book where every other page, and you're going to think I'm going to say has been ripped, but the bad news is every other page is ripped, and every other page is ripped, and then you end up with actually in a book where of 1,000 original pages, maybe you have 10. On top of that, it's written in a language that we don't quite understand, sort of hieroglyphics. And some of the words are also missing because they've been scratched out, so that's geology. People say, people in other natural sciences who use math rather than hammers, they say that geology is liquor and guessing, beer and guessing. But it really isn't, because we find oil and we find loads of stuff, we find minerals and water, and so it works. But it's dependent on a record that needs to be representative. And so this brings us to two things, sampling and representativeness. Would we find 4 millimeters 400 million years from now? Would we find even 30 meters? Would we visit that place? It's not everywhere. If you imagine dinosaurs, imagine Tyrannosaurus rex in the United States. How many of the skeletons are there? And how many Tyrannosaurus rexes lived? And Tyrannosaurus rexes lived for several million years. They existed not for 300,000 years or 8,000 years. They exist for several million years. And yet we have 10 of them. And sometimes just one bone. Also, the same is true for humans. How much of us will remain? Maybe not much. And in addition to that question is, will we be able to actually drill through it? So a civilization coming here would have to, one, drill the right place, and in that place where there is the moment now, would have to find actually something meaningful. Now, the thing that we think will work best is probably nuclear signatures in isotopes. So we have used nuclear bombs, particularly in the middle of the 20th century, and these will have left spikes. So the idea prevalent amongst geologists is that we are not a period, we are an event, and a really weird one, with loads of spikes in carbon isotopes, in nuclear radioactive stuff, and there will be weird materials in there, maybe some plastic. Some of this is explored in this book by Alan Wiseman called The World Without Us. He basically says, what if we all disappeared now? What happens? 1 minute, 5 minutes, 10 minutes, 1 hour, etc. So I highly recommend it. But you see how fast it goes. I took that picture in Texas of a road, and you see this road had been abandoned not even 5 years ago, and it starts to be colonized, and things disappear. So would we be able to find this is part one, but the next part that's also problematic is, would we be able to understand it? Even nowadays, we look at things from civilizations not so long ago, and we are hard-pressed to know, what does this mean? Why did they do this? Why did they scratch the surface in South America? And what is the exact meaning of certain types of writings? So in 400 million years, would people assign this to a civilization? Would they be able to understand it? And the answer to the Silurian hypothesis, probably not. And so the outrage of deep time is this, is that we have not lived for very long. We will probably not live for much longer. Evolutionary biology teaches us that. Even without we don't need to do anything. There's an internal clock ticking in species, and species come and go. And then there will be a record, which will be incomplete, and the longer we go, the more incomplete it will be. Until eventually there will be just a little bit here and there, and some alien geologist may come, and they may even find us, or our record, but will they understand it? And the answer is probably not. Funny, huh? And this makes me think of this picture. This is a very famous picture called the pale blue dot. Carl Sagan, the physicist, he was involved in a NASA program of the Voyager, which was recently on the news again, because apparently it still does stuff. And the Voyager is a probe, I guess, that's traveling. It's the farthest traveled piece of human thing from us. It's now at the edges of the solar system, and it has been for a while. And when they were decommissioning the program, Carl Sagan told the team, hey, would you turn the camera around and look at the solar system and take a family photo? which is very poetic. You know, scientists can be very poetic. And this picture is not of the family picture, but it's just of Earth. And you see a scattered light, a sunbeam if you want, and there's that little pale blue dot. It's smaller than a pixel. And it's slightly blue, and that's Earth. That's us, right there. And Carl Sagan wrote a book saying that. That's us. That's us right there. And it's the only home we've ever known. And I think, even though we're insignificant, and even though there's all of this deep space and deep time surrounding us on all sides, I think what we need to realize is that this needs to be cherished. Elon Musk, Jeff Bezos, right now, they have these sort of stories of going to other countries, as if other planets, excuse me, and ours is not that important anymore in their heads. And I would argue, and I think Carl Sagan tried to argue for that it really is. Aboard the Voyager, there's an audiovisual golden plate containing sounds and images of Earth. And I will say goodbye to you.
Hartelijke groeten aan iedereen.
I will say goodbye to you with the Dutch greeting.
Hartelijke groeten aan iedereen.
Thank you for your attention.
Mijn jongste dochter, ze is 4, had het deze week over vroeger, toen ze nog jong was. En ik dacht, jouw vroeger is mijn gisteren. En daarna dacht ik, en in jouw morgen ben ik al verleden. Mijn vrouw schrikt altijd een beetje als ze mijn leeftijd hoort. Alsof ze een beetje belazerd is. Want zo oud was ik helemaal niet toen we elkaar leerden kennen. Dus wat is er gebeurd? En ik snap het, ik schrik er zelf ook altijd een beetje van. Die 2 cijfers hebben niks te maken met hoe oud ik ben. Het is een getal dat in ons huis alleen fluisterend wordt uitgesproken. En zelfs dan liever niet. Het past in het rijtje woorden die niet genoemd mogen worden. JHWH, Voldemort, 47. Dus het concept van diepe tijd, waar ik al een beetje in geworteld lijk, spreekt mij erg aan. Omdat het relativeert hoe de zwaartekracht me tracht te grijpen en mijn vlees de grond intrekken wil. Want in de diepe tijd rennen bergen voorbij. Staan binnenzeeën met een knippering vol tranen om een hartslag later opgedroogd in brokken zout en fossiele vissen te verdwijnen. In de diepe tijd springen oerbossen de grond uit als sprieten gras op een lentedag. Om een zucht later tot stoppels geschoren een nageldunne sedimentenlaag te worden. Waaiend zand vormt continenten, sponsen laten zelfportretten achter in de kalk. Siluriaanse beschavingen kennen opkomst en ondergang. Zwermen plankton worden ineengedrukt tot zwarte massa om ons geraffineerd van snelheid te voorzien. In de diepe tijd krimpen tyrannosaurussen tot kip. Smelten eencelligen tot complexe levensvormen samen. Groeien vissen, vacht, voeten en verenigingsleven. En nucleaire massavernietigingswapens. De diepe tijd relativeert het vergilde verleden, waar ik steeds meer onderdeel van ben, tot een seconde in miljarden jaren. En in die seconde, nu ik het toch ben, blijf ik even bij de oude Grieken hangen. Die zich op een stukje nagel bevinden dat ik net afgebeten heb. De oude Grieken kenden naast Chronos, de personificatie van de meetbare tijd, ook Kairos, de god van het goede moment. Zijn god die heeft een enkele lok haar op zijn voorhoofd waar hij hem kan vastgrijpen. En als hij eenmaal voorbij is, zie je alleen nog maar zijn verdwijnende, glanzende achterhoofd. En ergens, tussen het goede moment en de diepe tijd, struikelen wij rond. Ongeveer een mensenleven lang. Tot wij zelf, ongezien, onopgemerkt gebleven, in een nageldunne gesteentelaag verdwijnen.